Hello, student. This is Mr. Teo again. Remember last week we talked about the chapter 2, and we talked about flow measurement using the orifice plate, and we talk also in the variation of it, like venturi tube, nozzle type, and then we went into the pressure measurement using barometer, U barometer, and we also discussed on the tilted sense of the U barometer, how to resolve the pressure calculation. And then we start to look at the level measurement using gauge glass, and then also we look at the ultrasound, how you use the ultrasound to reflect, and using the time of flight to calculate the distance. And also we touch base on something called the differential pressure meter using the head pressure on the high pressure leg and the low pressure leg. Now today we are going to continue the talking about this measurement sensor, and I'm going to share with you the slide in a while time, right?
For measuring temperature, flow, level and pressure. This week we will be spending some time to go through the control element. Let's watch a video before we discuss about control valves.
Any valve can be turned into a control valve simply by adding an actuator. Valve actuators, in response to a signal, move a valve to a desired position using an outside power source. These outside power sources may be in the form of pneumatics, electronics, or hydraulics. Pneumatic actuators move a valve's position by converting air pressure into linear or rotary motion. Linear motion devices open and close valves such as gate, globe, diaphragm, and others with a sliding stem to control the position of the flow control element. Rotary motion typically operates quarter-turn type valves such as ball, plug, and butterfly. A quarter-turn valve is one which can be opened 100% by turning the flow control element just 90 degrees. There are three types of pneumatic actuators: diaphragm, piston, and vane.
Okay, that's a quick introduction to basically the different types of control valves, right? Basically, we can look at the next slide.
Mostly the control element here we refers the control valves as shown in the video. Recall in week 1 we talk about control element as having transducer element and final control element. Here the transducer element for control valve will be the actuator and the final control element will be the valve itself. There are generally three types of actuators to be discussed here. They are namely the electrical solenoid type, the pneumatic type, and the hydraulic type. Basically, the transducer action is to convert either the solenoid, pneumatic or hydraulic signal into action of opening or closing the valve.
Okay, basically what is trying to say here, if you all understand what is a valve is basically an opening and closing of a pipe cross-sectional area. And then a valve is basically a device used to control the opening, right? And the control opening can be done by three means. And that's basically either is electric, pneumatic, or hydraulics, right? And as shown here, You have pneumatic, which is using air pump to push the piston so that it is shoved into the cross section of the valve and allowing the liquid to flow and not to flow. And then likewise, there is a solenoid type whereby you can energize it using the electricity. And of course, when the magnet gets energized, it will push down or lift up the piston. And at the same time, the passageway for the fluid to flow through will get blocked or unblocked, right? Now, likewise, for the hydraulic, basically, they uses the water. Pumping water in will push this section of the volume up, compressing the spring and therefore lifting up the piston, and therefore the water will be able to flow through this gap and going outflow. That means from the inflow to the outflow. So basically, these are the three types of action. Of course, the traditional one, it will be the mechanical type, whereby you tread the wheel clockwise or anti-clockwise to advance the piston or to open the piston, right? So that's the few type. Getting into the automatic kind of actuator, this is the plunger is actually the plunger or the stem is basically called the actuator, right? So we have three types: electric, pneumatic, and hydraulics, right? So
moving forward, we will talk about the final control element, which is the body of the valve itself. Valve opening and closing can be done by many methods. Here we are showing three methods. First method is the globe valve, which uses the plunger to open and close the valve. Second method is the ball valve, which uses rotation of the ball with a center bore through. When the flow is in line with the bore hole, the flow is maximum. When the rotation causes the bore hole to be perpendicular or hidden, the flow is entirely stopped. Third method uses the flipping of a coin-like surface. Flipper can be rotated to allow liquid to flow or not to flow. This last method is called the butterfly valve.
now this page is illustrating the previous page is talking about the way we control the plunger mechanism, right, of the valve. Now for this page, we are talking about the body of the valve, right? Of course, the body of a valve can come in different form. It can be like the plunger type, which we call this the globe valve. You got a dome shape, which plunge in and out, letting and stopping the flow. So this is what we call the globe valve. There's a balanced and unbalanced type. And then there is a ball valve, whereby the opening and closing is basically by turning, rotating this ball to be in line with the flow. It has a drill-through hole. The ball has a drill-through hole. When the drill-through hole is in line with the flow, the liquid has maximum flow. But when it is rotated in such a way that it is perpendicular to the flow, then the liquid get fully blocked, like for this case. So this is another, we call it the ball valve. So the plunger or the mechanism is basically like a ball rotating. Now the last type is the what we call the butterfly valve. It don't really look like a butterfly, but more like a coin. So as you rotate this handle, the coin will flip, right? Now when it flip to in line with this circle, that means the valve is actually 100% closed. Now other angle, it will allow different kind of flow rates. So that's basically these three types: globe valve, ball valve, and butterfly valve for the body, right?
Also for the final control element, flow characteristic can be depending on the shape of the plunger used. Some flow characteristic have flow percentage increase linearly with stem opening, while other can be parabolic in shape. The 6 flow characteristic are linear, equal percentage, fast, quick opening, square root, modified parabolic and hyperbolic. The diagram at lower left-hand corner gives you an idea that with different plunger head, different characteristic will be achieved.
So this is talking about the flow characteristic, right? Now, flow characteristic, basically we plot the flow percentage versus the stem opening, right? Stem opening, we talk about the area, for the percentage that is open. For example, if I leave this piston up, how much percentage is being exposed, and so is how many percent opening versus when it is fully open, right? Fully open, of course, is 100%. So basically, is the percentage opening versus the flow. So of course, for the linear case, we would expect 0. That means 0 opening will be zero flow, and then of course 100% opening will be 100% flow. So that is for the linear flow. So linear flow you might expect is like a straight line, but actually it's a dome shape. So as you lift up this dome, the area will increase linearly, and of course the flow will also flow according to the linear fashion. So that's the linear type, right? Now of course there is equal percentage, which looks something like the blue kind, equal percentage. And of course there is the fast opening, which looks something like, it's not shown here, fast opening. Quick opening, maybe the quick opening is the fast opening, which looks something like a red curve here. So a quick opening is, the shapes looks like that. If you lift it up, suddenly you will get a lot of flow through. So of course, in the total, the nutshell, there is actually 6 types: linear, equal percentage, quick opening, square root type, modified parabolic, and hyperbolic type. So these are the 6 types of flow characteristic that is available, right?
One important thing to note in the final control element are the failure characteristic, meaning in the absence of control signal, will the valve be closed or opened? Example, if we are using the pneumatic valve, in the absence of air, the valve is closed, then we call this a fail close. However, if the opposite is true, meaning in the absence of air the valve is open, then this is a fail open valve. Consideration of whether to use a fail open or fail close is very much tied to the safety consideration. For example, when fail to prevent hot water from flowing out and hurt someone, we close the valve. We use a fail closed. For valve sizing, we need to calculate the coefficient of the valve C. Generally, we need flow control because we either must flow rate W is accurate, flow rate Q such this is especially important in chemical mixing.
Sorry about that. I think I triggered the second voice, so the second sound, so therefore there was an overlapping of the sound. But nevertheless, let me roughly go through what is happening here. Now, first of all, you have the fail characteristic. Fail characteristic basically talk about at a point of failure. That means any device, when you fail, what should be the mode that it should assume. So if the valve fail, meaning that the controller got no control over the valve anymore. So what is the default? Is it default open for the valve, or is it default closed? So there is a default. So it's either is default open or default closed. So how do the designer of the valve determine whether it is fail open or fail closed? Now, for example, a pneumatic valve, when you say fail, means what? There is no air coming to it, right? So that it is fail. So if you talk about electric solenoid valve, so when it fail, means that no electricity is coming to it, right? Now, if you talk about hydraulic valve, that means when it fail, there's no water coming to it, right? So these are the 3 kind of possibility. Now, at the point of failure, should it be open or closed? It really depends on the design of the valve, right? And for the design of the valve, we always take into consideration of the safety at that point. Now, for example, your valve is controlling the hot water coming out into mixing with other things. It's a very hot water, it can scald anybody. Now, when it fails, do you think it should close or open? Intuitively, you would think that, hey, when it fails, it better close because it's a hot water, it can scald someone. So therefore, the answer will be fail close, right? Now, however, if it is putting a very cold water into a mixture which is hot, so then it must be fail open because you need the water to come out to cool down the hot structure. So really depends on the application, whether in that situation when it fails, which mode would be a safer way to design. So the designer has to consider about that. Now, the second part we talk about here is the valve sizing. Now, of course, when you design valve, you got to size it. You cannot just arbitrarily choose a valve. This one look nice, you fit onto it. Why do you need to size? Because first of all, there is 2 types of flow that you would be considering. Now, one of them is what we call the volumetric flow rate. So, and then the other one is called the mass flow rate. Now, volumetric flow rate, we are concerned about the flow, right? The volume flow. So for example, if you go to the toilet, every time you flush the toilet, right? And then of course, after flushing, it will fill up again, right? So there is a sensor says that detects the level and say that, hey, the level is low. So therefore they open the valve and let the volume get replaced. So this volume of water that is being replaced is what we call a volumetric sensor, right? It's replaced back the volume. So these are what we mean by volumetric flow. But however, for mass flow, usually we are concerned about mass when we deal with chemical mixing. For example, you try to mix 2 parts of hydrogen to oxygen, you get water, right? Now, can you have 3 hydrogen to oxygen? You cannot get water anymore, because 3 hydrogen and oxygen, even at the correct condition, temperature, etc., you cannot get water because it's not H3O, but rather it's H2O. So therefore, the mass of the mixing needs to be right. So therefore, in chemical mixing, usually you need to control the mass flow. Now, having said that, these 2 types of flow, we need to size, again, still need to size the valve in such a way. Why? Because the flow of, let's say, a water pipe, in the summer, the water will be in a liquid form, right? So the pipe, no problem, can flow. But in the winter, what happens to the water when it froze to ice? For water, the case is different. When it froze to ice, it will expand. And when it expands, what will happen to your valve? If you design just nice the size, you'll crack, right? You'll burst. So therefore, in order for this not to happen, you need to size, first of all, the valve properly. And of course, other consideration later, you will realize that we put in some extra measure to make sure that the valve don't burst. Okay?
Sizing of the control valve requires the calculation of the valve sizing coefficient CV. CV for different flow, example liquid, steam or gas, uses different formula to compute of the CV. In steam and gas flow, CI needs to be determined using the table given when the valve type is specified. KC can then be calculated with the given formula for KC. Excess capacity need to be factored into the calculation of CV. This is to take care of sudden increase in load or expansion due to temperature changes. Generally for flow control we use 150% more to the flow rate. Whereas for the rest of level, temperature and pressure control we will use 180% more for the flow rate.
So basically, in sizing of a valve, we deal with this parameter called coefficient of the valve, right? Coefficient of the valve, CV. Now, CV, of course, in any valve, you can design it for liquid, you can design it for steam flow, you can design it for gas flow. But of course, each of these different type of flow will means, because steam are very different from liquid and very different from gas, right? So as a result, empirically, they study and they realize that, hey, in order to size for liquid, you got to use this formula. In order to size for steam flow, you got to use this formula. In order to size for gas flow, you got to use, there's 3 different kind of formulas to be used. But out of these 3 formulas, of course, the liquid flow is the simplest, then followed by the steam flow and the gas flow, which is slightly more complicated. Why? Because steam flow and gas flow require another 2 parameters. One of them is called the CI, which depends on the valve body type, right? CI depends on what. So for example, if I'm using cage balance equal percentage, then my CI will be 31.5. Now, if I'm using butterfly valve, then my CI will be 20.8. So depending on which type of valve you're using, your CI will be different, right? So CI will be different, meaning that you plug in a different value for to calculate your CV, right? Now, second thing that they require is what we call the KC. Now, KC is also given as sine 3417 over CI times by the delta pressure over PI. Right, so this is another formula which is required to calculate KC, so that KC can be plugged into the coefficient of valve for steam and gas flow. Now, not to worry about all these formulas. All these 4 formulas will be given in the formula sheet, and even if the table is required for you to select the CI, the table will be given. So you don't have to worry that, hey, wow, this one is very difficult. because students usually react with all these things. Very difficult formula, and therefore I die already. Oh, no, don't die anyhow. Huh? Now, then for the, as I mentioned just now, when we size the valve, we always provide some extra measure. And this extra measure is to design, oversize it, because there's a tendency of the pipe might burst, the valve might burst, so therefore we over-design it purposely. So for flow control, usually we over-design by 150. So instead of 100%, we use 150%. That is, you multiply by 1.5 times. Now let's, usually we talk about the nominal rate. Now let's not talk about using the maximum rate. So we'll just ignore the maximum rate. Now if you are doing the level, temperature, or pressure control, then you use 1.8 times, which is 180% more. So a lot of time in the test calculation, I ask students to calculate the valve coefficient. They forget to include this excess capacity. So this one, it will not be given. So you got to commit to memory. Like for example, flow. You just remember flow is 1.5. If you see other than flow is 1.8 times. That's as simple as that.
SCADA, Supervisory Control and Data Acquisition System, is a system that uses multiple blocks hook up together to realize a comprehensive remote control and accessibility of data from the field. It requires sensor or manual input data which send or log in data into the system via PLU or RTU, remote terminal units. The SCADA network has evolved over the years from monolithic to the most recent being the Internet of Things, IoTs. At the control end, we have the human-to-machine interface. Software is available to fetch and plot the data trend for trending, diagnostic and management purpose.
Now, of course, this page talks about SCADA. I think you guys from the EEE side should be very familiar with this. This is what we call the Supervisory Control and Data Acquisition System. Now, this system is basically a kind of standard that is proposed by some gurus that include many sub-components joined together. Of course, on the first level, in the very end to the real application, we have the sensor and the manual input. A sensor is basically to sense the environment. And of course, sometimes sensor cannot be used, then you have to have human keying in the data, right? Once you have this thing, you will transfer this information to what we call the remote terminal unit, or RTU, or PLC, right? PLC and RTU. So basically, PLC is the programmer logic controls, right? And RTU, remote terminal unit. So data is then fed into the network. Now, network, in the early days, they used the monolithic independent type. Then they, as the technology improved, they go into the distributed LAN and WAN, then into network communication protocol, PCN. Of course, today it is moving very fast into the IoT, Internet of Things, right? So like cloud computing and IPv6, right? Of course, then, of course, from that network, you would, at the receiving end, you would have the human machine interface, which is the SCADA panel view for those people that require this information to be able to access using some SCADA software program to check the trending of certain information so that they can do control, right? And then, of course, in the computer side, you have a human machine interface, right? Etc. etc. So that's basically it. Okay, so this page is pretty simple.
With that, we complete chapter 2. Please proceed to do watch the tutorial.
Now, this is
3.
the last part of chapter 2. So now I will proceed to tutorial 3, and we will look at first of all from question 6, question 8, question 11, question 9, and question 10. Of course, each of these questions will address to different part of the things that we have studied. Of course, question 6 will talk about differential pressure, and question 8 will be the probe, capacitive probe, and question 11 again differential pressure using the H rho G, the heat pressure, and question 9 will be the valve selection, and question 10 will be the selection criteria. Now let's look at first of all question 6. Let me start to share the screen of where is my Okay, this should be the one, right? No, this is the not the one. Let me share again. This is then the one. Okay, so today we are going to talk about, first of all, is the question 6. Now, question 6 says that there is a differential pressure transmitter that are commonly used to measure input level. So input level is here, or to determine the range of the transmitter range of the following arrangement. So basically, what is the sensor here? It's a differential pressure sensor. You got a high pressure leg and the low pressure leg. So it's mounted here, right? So usually for differential pressure meter, the level is very important. So all the measurement will start at this level where the differential pressure meter is mounted. Any level that is below, for example, this 200 millimeter, we don't consider. Any other things that is below it, we don't consider, right? Of course, the end, so the start, you can guess right now, the start of the level measurement will be from this point here, this level. Of course, the end of the level measurement will be determined by the level of the reference, right? Reference leg. This is a reference leg. By the way, the left leg here, or the low pressure leg here, is actually the reference leg. So the highest the liquid tank can go is when it matches the reference leg, right? So therefore, the range of transmission will be from 200 millimeter to this should be 1000 millimeter, because the length is 1000 millimeter. So there is extra 100 millimeter, which is no use. So there is some wastage here. The range is not covering the 100 millimeter and 200 millimeter range. So then how to calculate this? Okay, let's go to the whiteboard. Now you have a differential pressure meter. So this is question 6. Let me write the question 6 here. Okay, you have a differential pressure meter that is mounted. This is the low pressure leg, and this is the high pressure leg. It's actually no problem whether it's a low pressure leg or a high pressure leg. So there is this reference leg, which is filled with what we call the, is it called the reference liquid? We call the wet leg, wet leg. Okay, and of course, sorry, I accidentally draw this. Right, and then of course it has some housing here, whereby it goes into the tank. Right, so the tank is basically also here, touching the low pressure leg, I mean the high pressure leg, and this is your tank all the way to the top, right? All the way to the top. Now, of course, like I said, the lowest reference for the differential pressure meter, this is your DP. This guy here is your DP, differential pressure meter. It will start from this reference level, which is the low level, right? Reference level. And it will go all the way up till this level, which is dictated by your reference leg. So the start to end of transmission will be along this level, right? Start and end, whichever one you define it as a start or end. So this is a differential DP, not PP, DP here. Okay, so now it is stated here, below here 200 millimeter is no use, because it is below the DP. 200 millimeter actually got no use. And of course, above here, there is 100 millimeter, there is no use. No use. Also, these two are no use. So what is useful is only between this range. Now, if the, and then of course, all the pressure will be calculated using the head pressure. So pressure for head pressure is given by height times by rho of the liquid times by gravitational pull. Now, so let's calculate the pressure. Of course, the differential pressure will be given by differential pressure, delta P will be given by pressure on the high pressure leg, minus by pressure on the low pressure leg, right? So what is pressure on the high? Let's say I assume this is the start. I assume this is the start and this is the end of the measurement, right? So the level can move from the start all the way to the end. Now, if there's pressure at the start, so at the start, at start, what should be the high pressure leg? That means the liquid is only filled up to here, right? Fill up to here. So what is your delta pressure for this guy? At the start, of course, there is zero height, right? So it will be 0 times by the density of this liquid, rho liquid, right? Rho liquid times by gravitational pull, right? So this is your P high. This guy here is P high, right? Now minus by low pressure. Low pressure is the reference leg. Remember here is 1000 meter, 1000 mm. 1000 mm is actually 1 meter, right? So is 1 meter, height is 1 meter times by rho, which means the density of this liquid here. So do they have the same liquid? I would think so, because they seems to be sharing the same liquid. So we assume that it's sharing the same liquid, so is rho liquid again times by G, right? So what is the density of the liquid? Now, what is the density of the liquid is not given. Only the specific gravity is given. Now, specific gravity of a liquid will be density of the liquid divided by density of H2O, water, right? So if specific gravity is given is 1.1, then what happens is rho liquid will be given by, because density of water is 1000. So you just bring over, this implies that rho liquid is actually 1100. So then this rho liquid will be 1100 for both cases, because they are using the same liquid. Of course, then your G will be 9.81 gravitational force, 9.81. Right? So for this case, you would be able to calculate, right? So the first one here, of course, this is the low pressure leg. This is the low pressure part, right? Now high pressure part, because the height is 0, so therefore the term will be 0, right? And then the low pressure leg will be minus 1 times 1100 times by 9.81. So essentially you will get let me see, you will get minus 10.78 kPa. So this is your start, at the start. This is at sign, right? Now what about at the end? At the end, of course, your delta P is calculated differently. Now you have height, you have height of 1000 as well. So this is again 1000, right? Multiplied by rho liquid is this is 1 meter. 1000 is 1 meter. Multiplied by rho liquid is 1100. Multiplied by G is 9.81. But on the other hand, the left rig also is the same thing. 1 meter multiplied by 1100 multiplied by 9.81. So as a result, your at the end is actually measuring 0 kPa. So your range of transmission is from start to end. So your range of transmission will be actually from 0 kPa to minus 10.78 kPa. Okay, so that is for your question 6. Okay, I don't know whether I'm too fast, but I'm okay, because for video you can play back. So therefore, I'm not too concerned about this, right? So you can always stop and replay back. So now let's continue and take a look at the question, the next question that we need to discuss, just to save some time. Now the next question we need to discuss is, of course, question 8. Now question 8 is talking about the capacitive probe. Remember the capacitive probe that we discussed in the previous few lessons. And of course, what is the formula for capacitive probe, if you can recall? What's the formula for capacitive probe? Question 8, for formula for capacitive probe, right? So formula for capacitive probe is, let's go back to the whiteboard. And of course, I have to clear this. Later you can rewind and check it out, the answer again. Now, of course, capacitive probe C will be equals to CA multiplied by 1 plus, what is your, I think it's KL something, LX over LD, LD over LA or something like that. Let me check the actual formula. Let's go to the blackboard. Let's go to the blackboard and look at the tutorial sheet and look at the formula sheet, right? And take out the actual formula, just in case everyone is confused. So let's share the formula sheet. Where's the formula sheet? Formula sheet is here. Let me share. Now let's look at the capacitive probe. So where's your capacitive probe? Thermocouple here. Gas field, ultrasound is given by this guy. So it's CX, CA, KX, LX over LA. So let's go back to the whiteboard again. So it is actually CX equals to CA. So this is CX. I was guessing it partially correct. Equals to CA plus by KX over LX LA. Now what is all these terms? Okay, let's take a look. KX is the dielectrics of the liquid. This is dielectric. LX is the length of the probe immersed. So if you have a probe, right, that immersed into the liquid tank, this length will be called LX, right? And then of course LA is the entire length, right? LA is the entire length. The probe LA is here. And then of course CA is your capacitive at air. So it's the air capacitance. Without submerging. So this is without submerging capacitance. And of course, CX is your total capacitance. Now, after knowing all this definition, we take a look back at the question again. Take a look back at the question again. Sorry, not the question. This is not the question. The question is here. Now the question again, it is 1.3 meter long. So that means this is LA, right? LA is 1.3. Capacitance of air is 31 picofarad. So this is CA. And it is submerged in the water, partially submerged in the water. Dielectric is 80, this is KX. And of course, the capacitance is 0.97 nanofarad. So this is a total capacitance reading. So they ask you what is the probe of the length immersed. So let's go back and substitute. Go back to the formula that we created just now and substitute. So you have CA equals to 31 picofarad. So this guy is 31 picofarad, right? So that's 31 picofarad. And of course, you have the dielectric is equals to 80. Sorry, I should delete away this line and this line probably. So the dielectric we know is 80. So this guy will be 80, right? So this guy will be 80. And of course, the other one is the total capacitance is 0.97 nanofarad. So this is given, this is given, this is given. And of course, the total length of the probe is 1.3 meter, right? As specified just now. So this is 1.3 meter. Oh. So we've all given except LX, which is the level of the amount of probes that is submerged. So they ask you find LX. Right, so of course LX can be found. So you just need to rearrange this equation. So if I do a quick one, the rearrangement will be LX will be CX over CA. LX will be CX over CA. CX over CA. Sorry, it's not CX, just CX over CA. It is. I just do a quick mental one. 1 minus Cx over Ca, and then you multiply by Kx over no, Lx you don't multiply by Kx. Sorry, my mental not working. Okay, basically, if I want to find Lx, I would need to Cx divided by Ca. Then I bring the 1 over is minus 1. Then, of course, I got to divide the whole thing divided by Kx and multiply by La. So your Lx will be something like that. So you fill in what is La. La is 1.3 meter. Fill in Kx is 80. You fill in Cx is 0.97 nanofarad. And this guy is 31 pico. So you punch your calculator using this, you will get Lx equals to 49 cm. Or in other way is you divide by 100, so it's 0.49 meter. Oh, so this is for question 8. So this is for question 8. Answer for question 8 for the capacitive probe. Right, so quite interesting question. Now, let's look at another question, which is it this page? No, it's another one. Let's look at another question, which is question 9. Now, question 9 talks about CV. Just now we just study about the control valve. So they talk about control valve sizing, right? How you size your control valve, and given all these parameters, and of course the answer is given as 752. Maybe for this I would just share the solution. Okay, so for CV for steam, so I presume that it is using for steam. So the formula is straight away can be lifted from the formula sheet, right? So you have this chunk of things. But of course, remember for steam flow, you need also to determine your CI and your KC. So CI, of course, if you read the question again, you would be able to determine that the CI is actually cage unbalanced type equal percentage, right? Let's look at the question again. So the type of is a cage type, right? Cage type equal percentage, right? Equal percentage unbalanced. So if you go back to just now that page, so you have cage type is here, unbalanced equal percentage. So therefore you can see the CI will be given by 35.3, 35.3. So therefore you can straight away leave it from the table there. Now, of course, after you find your CI, then you got to plug in, for example, the PI and P input and pressure input and output is given, so your delta P you will know. So you plug in your delta P as well. PI is here and CI is there. So therefore, with all these, you plug in to solve for KC. And with KC and CI, and then of course mass. For the mass, you got to have extra allowance. Remember, this is steam flow, so we multiply by 150%. So it's 1.5 times in excess. So instead of using the original mass of 1.3, we use 1.3 times by 1.5, right? So with this, everything factored in, then you do a calculation. And of course, let me see if they have the solution for it. No, so basically with this, if you plug in all this value and calculate, so basically you should get the answer of CV equals to 175.1. Okay. Now, the question actually tells you the mass. Yes, the mass flow rate. The mass flow rate is W is actually 1.3. Right. So basically, using that formula and then plugging in, you should be able to find. Are you confused? Or maybe I should demonstrate also how to solve this. So again, I always like to start by looking at the formula sheet. Now, formula sheet says that the valve coefficient, you want to see the valve coefficient sizing, you got to search the page such that you can find the coefficient of sizing for valve. And of course, it is here, right? So it's for steam flow. So basically, your formula is already straight away given. So you just need to copy this formula and this formula out, right? And of course, the table for CI is given. So you just need to copy this guy. So what happens is, if I were to copy out this guy, so what is my CI? My CV is actually, okay, my CV is actually, I also cannot remember, 78.8 times by 10 to the power of 3 times what? Times mass flow divided by CI KC, and then of course last but not least is the square root of input pressure PI multiplied by the rho, the density. Now let's find each of the components individually, right? So just now from the table, CI is equals to what? CI is equals to 35.3, right? Using the correct type. So this is CI is 35.3. This is from the table, right? Now, of course, the mass we cannot use directly as 1.3. So this one you got to include the surplus of 150%. You got to multiply by 1.5. So the mass is actually 1.3 multiplied by 1.5. Right? Now Kc has another formula, right? So what is the Kc formula? Kc formula again just now is given in the data sheet is sine 3417. This is sine 3417 over Ci, I think. Over Ci, and then multiply by square root of delta P over Pi. Delta P over Pi, rho or Pi? Over Pi. Now P input, we already know, right? P input we already know from the question is 420 kilopascal. So this is 420 kilopascal. Now what is delta P? Delta P is Pi minus Po, right? So Pi minus Po is 420 kilo minus by what? Minus by 250 kilopascal. So that gives you 200. Let me punch my calculator. My mental calculator a bit slower now. 420 minus by 250 give you 170. So this is actually 170 kilopascal. So you have the delta P. This is actually your delta P. Yeah? This is CI. CI already known is 35.3. So basically you can solve for KC. This is KC. Right? So once you solve for KC, you plug in. Again, your PI you already known for here, 420. And your rho. What is your rho? What is your density? Density is also given in the question is 1.9 kilogram. This is 1.9 kilogram per meter cube. So everything is known. So basically you can just solve with all the parameters known. You can just solve for CV, and if you calculate punch your calculator correctly, it should be 175.2. Right? So this is part A of question 9. Part A of question 9. Right? Now how about part B? Should the control valve be air open or air closed? Air to open or air to close for the process, and why? Now you are dealing with a control valve that control a boiler steam. right? Boiler steam means that when it fail, that means no air, right? Fail means no air, right? Fail means no air. Should it close or open? I would say no air. No air means what? Close, right? Because it contains steam, right? No air means fail, right? So it's fail to close. So this is a fail to close kind of valve that I'm looking at for safety purpose. Oh, so it should be fail to close because what's the reason? Because we do not want steam to come out to hurt someone. Right? So that is the design consideration. Okay. Now next we go to the next question, which is question 1. Let's go to the question again. Now next we look at question 10. Question 10, what are the factors to consider when selecting above? This is a theory question, so very straightforward. I will go to the solution and see the theory. So the factor to consider when looking at a sensor are accuracy. This one you can find in your detail write-up in your lecture notes. So precision, sensitivity, dead band, and reliability. I shall not go through it. You can read it yourself. It is self-explanatory. So question 10 is pretty straightforward. Now let's go to the next question, which is question 11, right? 11 is a bit difficult. It's a bit more complicated to solve, right? Now, 11 has many parts, but is dealing with again your differential pressure meter. So this is the differential pressure meter. Remember, for any DP, the level is very important, and we are always using H rho G. Now H rho G. So the one that is touching your high pressure leg and the low pressure leg. So these are the point, right? These are the point that is touching a high pressure leg and low pressure leg. Of course, the lowest level will be here, not there, not this level. The lowest level will be here, this level, at where it sit, where the DP sit. And of course, all these height are all given, HU, HV, etc. And then of course the rho density of the fluid here, density of the gas, density of the vapor, right? V, is there a density of V? Rho V is the compensation leg. So this is a rho V, right? And then, so they ask you to determine this at the start of the measurement. What is PU at the start of measurement? What is the pressure, right? And then what is the at the end of the measurement? What is the PU at the end of the measurement? So they say that at the start of the measurement, the level is at HU. So at the start, it is at HU. So it means it's at this low level, right? At the end of measurement, it is at HO, not the hard maximum. So it starts here, it ends here, okay? And then tell the question, the questioner, the examiner, what is the range of the span of the differential pressure meter? What's the range of span for this case? So okay, basically you need to familiarize yourself with the entire setup. So maybe we should also do the question together, right? I think I can clear this, and then I start drawing my drum. There's a drum here. Okay, there's a drum here. Right, this is your drum that you want to measure, and of course it has two going into the 2 points of the differential pressure meter, right? So the differential pressure meter, you have high pressure leg and low pressure leg, right? High pressure leg and low pressure leg, and of course this is your reference level of your DP. This is your DP. This guy here is your DP, and then of course measuring from here, the first level is what we call the HU. HU is actually, I just put it into as 1.3 meter because it's already given 1.3 meter, right? And then of course the other one is the HO. HO is the end of measurement, which is HO. Now HO is given as 2.7 meter. So this guy here is 2.7 meter. It's 2.7 meter, right? And then of course, then you have a HV, which is 3.75. Is actually at this end here, to the reference. This is actually 3.7 meter. Okay, so it's 1.3, 2.7, and 3 something meter. Now, of course, there is in terms of the density, you have rho g here. Of course, this part here is the liquid, and this part here is the liquid, right? And then this is the gas. So rho g is your gas. Rho g is given by 1.25. And then, of course, there is rho FL, which is the rho fluid. Rho fluid is given by 930. And of course, there's another rho V here, rho V, which is the reference lake. They fill it by another fluid. Rho V is given by 1.25 again. Now, so at the start of measurement, at start of measurement, we have delta pressure will be equals to, let's say, pressure of high lake minus by pressure of low lake. Right? What is pressure of high lake? Pressure of high lake will be, now the pressure of high lake at the start of measurement will be this guy, right? Sorry, the entry point is actually here. It's not turning at here. It should be turning at here. So it will be here, right? So what is your height of the liquid H? H will be 1.3, right? 1.3 meter. Rho will be rho FL, right? The liquid will fill until the bottom here. So it's a rho FL times by G, right? Of course, that is the fluid side, but what about the gas side? Of course, if you don't fill by the fluid, the rest portion will be filled by gas. Huh? So the gas side will fill at minus by the gas, right? The gas will fill at the height of 3.7 minus by 1.3, right? That's your height. 3.7 minus by 1.3, which means that this whole length here will be filled by the gas. Then you have the rho gas, right? And multiply by G. Now rho gas is 1.25, right? Then of course all the G will be 9.81. So the G is 9.81. Both of the G, this G and that G. Now rho FL is 930. So you plug in, you would find that the delta P, which it will be about answer will be about 11.844 kPa. Right, will be 0.844 kPa. Now at the end, of course, the measurement goes all the way to the end. And it means from this level, you will shift all the way up to the center level, which is the HU level, right? It's a HO level. This is a HO level, right? So the end of measurement is at HO level. So at end of the level, then delta P is again P high minus by P low. Now the P high right now is slightly different. It's no longer 1.3. It is increased to 2.7. So this guy is changed to 2.7 meter, right? Multiplied by rho is again rho FL, rho of the fluid times by G, right? So this is your high pressure, but the low pressure lake will be remaining the same, right? Of course, I forgotten to, I forgotten to include the gas. So there's some error here. Maybe I should delete this part here. This one I got to recalculate. I forgotten to include the gas. Okay, so maybe I should put here the high pressure lake is 1.3 times by rho FL, which is the liquid, times by G, and then the gas is still on this side. So it's plus by 3.7 minus by 1.3 times by rho gas times by G. So this is still on the high lake, on the high side. This is all acting on this side of the lake. Now the other side of the lake, the reference is minus by the reference lake. Reference lake is again, this is of course the full height of 3.7 minus multiplied by rho V and multiplied by G, which is 9.87. Then you will get this. So just now forgive me, this is the gas I put on the wrong side. It should be at the high leg side. Now same thing here, you plus by the gas acting, but now the gas will be much smaller. It's actually only 3.7 minus by 2.7 instead of minus by 1.3. Then you have a rho gas, a G, right? Rho gas G, and of course minus by your 3.7 height of your reference leg, multiply by rho V and G. So with this, you should calculate and you will get around 24.599. So this is 24.599 kPa, right? So of course, so then the range of transmission will be, of course, from 11.844 kPa to 24.599 kPa. And that is for your question. This is question what? Let me take a look. This is for your question 11. Oh, this is for your question 11. Okay, do we have any more thing not answered for question 11? Okay, that's basically it for question 11. Right, let me just get a quick check. Okay, basically with that, right, we complete all the sharing for all the tutorial question that we set out to do. So basically with that, that will be my end of the section. I wish you all the best, and I think it's for certain of the question is quite intensive. Maybe you can replay and take a better look, closer look at it. And if you have any question, you can always come and look for me. With that, I thank you. I will stop the video now.